like to welcome you all to this edition of Airtime Seminar Series. I would like to introduce Dr. Mark Hansen. We are lucky to have such an illustrious professor of civil and environmental engineering from UC Berkeley here today with us. He graduated from Yale with a bachelor's degree in physics and philosophy and has a PhD in engineering science and a master's in city and regional planning from Berkeley as well. And since joining the Berkeley faculty in '88, he has led transportation research projects in urban transportation planning, air transportation systems modeling, air traffic flow management, aviation systems performance analysis, aviation safety, aviation environmental analysis, and air transport economics. And so today's talk will be on irregular operations, flight delay and passenger delay, and some evidence in said area. So thank you very much.
All right. Well, thank you for having me. I guess people can hear me okay in the on Mars or wherever they are. So yes, thank you a lot for having me today. And my co-investigators are listed here. But I also want to acknowledge NASA, and particularly the NASA University Leadership Initiative Program, and for making this work possible. And I'll be speaking more about that in a minute. I particularly want to acknowledge Husni, who is our, what's your official title?
Technical monitor.
Technical monitor. So he's been monitoring very well. And so he's also contributed to this and feedback on earlier versions of the work. So before I talk about the immediate topic, I want to introduce people to CATRes. This is what we named our University Leadership Initiative. Stands for the Center for Air Transportation Resilience. And the idea for this effort came about, I think it was 2023, January and December, maybe January 2024, where there was a famous meltdown at Southwest Airlines due to a winter storm, and the airline sort of lost track of where its pilots were, and there were many people that had extremely long delays and had to abandon their holiday travel plans and so on. And then as shortly thereafter, in early, I guess it was 2024, there was the NOTAMs shutdown. And so that was turned out to be a short duration event, but there was a total ground stop in the NAS for several hours. And things like this kept happening. And so we became interested in what we can do to make the system, the aviation system, more resilient to these various kinds of disruptions. And as those examples illustrate, the sources of the disruptions come from many things. Weather is obviously an important one, whether convective weather or winter weather. And then increasingly IT type outages like the NOTAMs or CrowdStrike, which was also, that was the summer of 2024, I guess. Yes, is another example of such a major disruption. So one thing that we did early in the research, and I'm using it here a little asynchronously in terms of sort of motivating the proposal, although we did it after the proposal was successful, was we just looked at what the prevalence of disruptions are, how we can categorize them, And so some work that we did last year clustered days in the NAS starting in 2010. So we look at things like cancellation rates, arrival delays, departure delays, airborne delays, and we do it on a geographic basis. So we have some spatial intelligence as part of the data set. And then we just look for similar days using a couple of methods. One is k-means and the clustering, and the other is anomaly scores. You were talking about anomalies on Mars, and so we look for anomalies on Earth. So if we look at all the days in the NAS, we find that about roughly over half of them we classify as smooth, where things run quite well. But on the other extreme, about 9% of the days since 2010 have been disrupted. And these disruptions include all the ones that I mentioned in the previous discussion and various other ones. And those disruptions have different subcategories. We have 4 subcategories. Some of them are kind of regional, but they propagate enough so that they affect the entire system. The others are kind of NAS-wide. And so the highlighted clusters in the bottom of the table are the ones that are the days we're focusing on in our research. And one thing that we found is that those disrupted days or disruptions, which are sometimes multiple days, have been increasing in prevalence since 2010. So here's some evidence of that, just going back and looking at the days that we clustered in the previous slide and simply looking at when the disruptions occurred, what days they were. And we see that if we look at disrupted days, there's a big jump after 2019. And if we look at the number of disruptions, which counts each disruption, even if it's multi-day as one event, then that also has increased. There's evidence there, a little more evidence that it was increasing prior to COVID. So it's not just simply a COVID-related phenomenon. But we've also created at the top here what we call a catalog of disruptions, which are kind of the gist for subsequent model development and other analysis. So because we made the case that disruptions are an important problem and that they are increasing, we have this sort of vision, which is, oh, hi, how are you? We have which is to kind of think of resilience in a manner analogous to airline safety. And so we know that airline safety is produced by combining airline and government overseers to identify and mitigate risks before they lead to catastrophic accidents. We would like to sort of do a similar thing to improve NAS resilience by identifying vulnerabilities of the system to disruptions and then how to mitigate the disruptions. So that's kind of the big idea behind our particular ULI, the CATRes ULI. And this is a large cast of people from around the country. It includes 4 major universities, a couple of other universities that also play important roles. It includes several companies, and it includes among the companies some of the airlines, and also we have FAA participation. So that's the kind of big picture about who we are. And these are our research objectives to what we call stress testing the NAS to basically evaluate and identify vulnerabilities and The second objective is to try to harden the NAS against those vulnerabilities. And then the third objective is to kind of preserve the nature of the work that we're doing past the time when the ULI ceases to exist as an entity. So continued monitoring and so on, trying to think of what is the right institutional framework so that there can be sort of continued efforts to identify emerging sources of disruption and try to mitigate them. So our overall research has these three components, as I just described, and this gives kind of a big picture about what we're doing. And the first column is that first research challenge, so what we call stress testing. Then the second column is the hardening, and then the third column is the sustaining. So those map exactly into the three technical challenges that we described earlier. And then situating what I'll be presenting subsequently in the context of this larger effort. The highlighted box is what will be the source of the subsequent discussion. So now we're going to focus on that gold box. So passenger delay in the NAS. So this is kind of the core technical presentation. And so obvious fact that I think people in this room certainly acknowledge is that the commercial aviation system is designed to move people. I guess we should say people and goods to be complete, but we're focusing on people here and not airplanes. And ironically, perhaps understandably, when we think about the performance of the system that's in terms of the data that's widely available, what we know about is the airplanes. We don't really know much about what happens to the people except anecdotally. So we are basically trying to address that by developing a model for passenger delay that will be used in the different efforts I described in terms of stress testing and hardening the NAS. So we want to see to what extent, particularly in these irregular operations type days, we can improve outcomes for passengers. That's kind of the ultimate goal. So I have to say a little bit about delay. I remember the very first time I spoke at in this building, maybe 25, 30 years ago, and I was giving a talk about what happened at Dallas Fort Worth after they added a new runway in 1996, I think it was. And I went off about how I thought delay was a terrible term and that we shouldn't even use it because it's not clear what your kind of what your baseline is for looking at delay. Ironically, I was an hour late to give the talk, so that did not go over so well. So what we'll be using this term, and we're just trying to be explicit as we can about what we mean by it. So delay can mean different things. It's an excess duration of some flight phase against some ideal, like taxi out time or airborne time or whatever. Or it can be the lateness of some event compared to some target time. And we focus on that second type of definition here. And we're particularly focusing on arrival delay against schedule. So our baseline time, our target time is the schedule, and the time relative to that is the delay. And although we've shown on the right kind of what this looks like from a standpoint of a particular flight, so flights have a scheduled block time. One of my other hobbies is to just try to understand how scheduled block times are set, by the way. So the green is the ideal in the schedule, with the scheduled block time being the length of the green bar. And as we all know, sometimes flights arrive after they're supposed to, and that's arrival delay. Sometimes they arrive before as well. So clearly this is straightforward for flights. It can also be used for passengers, with the exception that we have to recognize that they're often traveling on more than one flight. But as far as having a scheduled time of arrival and comparing when you arrive compared to that, we can do that for passengers as well. So passenger delay versus flight delay. When we think about these, in some cases they're the same, and in some cases they're not. So when is an arrival delay for a flight similar to the arrival delay for a passenger? So if they're on a nonstop flight, that would be the case. Or for passengers who make their connections and then arrive at their and are flying on their last leg, the arrival delay of the last leg flight will be equal to their arrival delay. But then there are these other cases where the flight delay and passenger delay are different, and they can be different in different ways. So a connecting passenger on their first leg, if that flight is delayed and they make their second leg, then in many cases that first leg delay just disappears. It doesn't matter in terms of when they arrive at their destination. At the other extreme, if they don't make their connection, then that delay will become very, very large. And that's an example of a disruption. And that's going to be a large part of our focus here. And finally, cancellations are another example where passengers incur a very large delay. So we have some data to look at. As I said before, one of our challenges is that while flight data is very widely available in terms of ASQP and other databases, we can look at when flights arrive relative to schedule or various other things. Passengers is much less commonly available, but because of the interest of different airlines, in particular one of them in our effort in CATRes, they agreed to provide interesting data set, and I made some token effort to de-identify the airline here, but you'll know quite quickly what it is. And so what they did is provide 2 days in 2019. So this is a newish. It's not super new, but it's the newest that they would be comfortable providing us. And they're both IROPS days, disruption days. They appear as such in our cluster analysis, for example. And each data set is about 6,000 rows of data, and each row is a leg of an itinerary. And what it includes, and when I say itinerary, I mean, of course, a passenger itinerary, and it includes both planned and flown arrivals and departures by that passenger. So we can use this data to do things like identify misconnections and cancellations, and when passengers actually arrive at their destination compared to when their original itinerary would have had them arrive. So in the next, I'll show you next, just to help you visualize this data structure a little bit. So this is just three of whatever it's like 600,000 lines. But so there's a passenger ID, and there's a planned departure time and a flown departure time. There's a number of connections in the itinerary, and in this case, they're all one connection itinerary, so nonstop flights are not included in these three. And then there's a sequence number, which is typically 1 or 2, although occasionally it may be more for longer, more double connection itineraries. And then there's a planned arrival time and a flown arrival time. And there's also, we can see whether the passenger had a missed connection or not. Was their flight the same in the planned and the flown? And so that's the kind of raw material for the subsequent analysis. And here are some just general statistics. So we have about 400,000 or a little more than that unique travelers, and we have 1 day in July and 1 day in August. So that's what the July and August refer to. And of these, there are about 4,000 misconnections, and there are about 2,000 itineraries with cancellations. There is an average passenger arrival delay, including not just these disrupted passengers, but the ones that have not experienced these things, of about 25 minutes. If we quickly go down to the bottom row here, if we just compare the passenger arrival delay to the flight arrival delay, we see it's about twice as much. So just as a rough rule of thumb, if you look at arrival delay on a particular day, you can kind of double it if you're going from flights to passengers. But there's much more to the story for passengers, because the delays for passengers are really focused on a small number of disrupted passengers that really get major delays. And there are two categories of these disruptions. One is average arrival for the misconnection passengers, and we see that's about on average 6 hours of delay. And for passengers whose initial itinerary involved a flight that is turns out to be canceled, that's about 5 hours. So you have these passengers that really get nailed by these kinds of disruptions. So we'll just visualize the data in a few different ways before we get into the actual sort of modeling piece. So this is one way of thinking about it. So a big driver of these disruptions will be first leg arrival delay. So flights going into the connecting hub that don't get there on time, and therefore cause the passenger to be unable to meet their second flight. So we emphasize that we present that in the x-axis, and then we look at the flown trip arrival delay on the horizontal axis, on the vertical axis. So this is when the passenger arrives at their final destination relative to the scheduled time. And there are sort of two cases here that are quite different, as we talked about before. We said when are the delays the same and when are they different? And so the single leg flights, they're exactly the same. Nice 45-degree line. By the way, the first couple of times there were some points not on this 45-degree line, so we were wondering what was going on, and my student diligently figured out what that was. But as we'd expect, the blue line is just a boring 45-degree line. And then the gold is the connecting passengers, and there are many situations here. So generally, all the gold is what we call double leg here, a connecting passenger. Then the different shapes indicate different scenarios that these passengers might incur. Of course, they might just make their connection, as we talked about before, so they would also fall on that 45-degree line that we just were discussing. Some of them just miss their outbound flight. It happens. People go to the airport bar waiting for their flight and drink too much and forget, which can cause their bags to have to be pulled. We did a whole study on having to pull bags from passengers who get drunk at airports. And then the ones that are a little more our focus here. So we have canceled flights indicated by the triangles, and we also have missed connections as another example here. So basically, the bottom line is that there's this complete kind of lack of correlation between flight delays and passenger delays for connecting passengers, and that's what the gold dots tell us, and then more detail we can get into when we will get into. This is the same story for August. Doesn't look that much different. Another thing that we can do, just sort of in an exploratory way, is we can look at the arrival delay of the inbound flight and look at the OD delay in these cases where they did not miss the connection and where they did miss the connection, and also what fraction of the connections were actually made. And we see sort of part of those, the major buckets here. And so we see consistently, of course, there's much more delay if they miss their connection, and that the fraction of people that make their connection is less as we increase the inbound arrival delay. Here's another look at it, this time by airport. And so again, the blue is not missed connections. The green is, so the gold is the missed connections. The arrival delay is the arrival delay of the inbound flight, the first leg flight. And we see the expected layover in the on the horizontal axis, and so on the vertical axis, and then we also see major differences there, and we also see these kind of lines between making a connection and not making connection, and those slopes are somewhat similar but also somewhat different, and they're also different from month to month. So even if we look at a particular airport from one day to the next, exactly what the kind of threshold is for missing a connection is not uniform. And finally, if we, again, emphasizing the fact that a lot of this delay that these connecting passengers will face will be as a layover. So if we look at the expected layover versus the realized layover at the hub, at the connecting airport, if they make their connection, it's follows more or less a 45-degree line. But if they don't make their connection, we have much higher layovers that translate eventually into arrival delay. Okay, so that's just kind of a pass through the data, looking at some general patterns. And now we'd like to focus a little bit more on how we can model this and what are we really trying to do. So we have these two kind of precious days where we have this unique data, and the goal is to use that data to build a model of passenger delay that can be applied on other days where we don't have this very unusual data. So we want to be able to use publicly available data as input and predict passenger delay, not just for these two specific days, but for any day where we have the flight data. So this is the way it's going to work. So we have the publicly available flight data. We have also publicly available itinerary data at the not at the flight level, but at the from airport to airport level, segment level. So we have those two sources, and then we need to first have a model that takes those data and actually creates itineraries for flights that are flight specific. So that's the itinerary assignment model. And I won't really be talking about that here. We haven't really started doing that yet, but we'll also be using this data for these two days as a basis for creating that assignment model. And then the other part, which we will be focusing on, is using that same data for this passenger delay model. So basically taking what we know about what passengers are flying, what itineraries, and what happens with the flights in terms of their delays, and predicting a passenger delay. So this is the little more detail for the delay model structure. So we have this itinerary assignment model in the ultimate product that we're developing. In this case, we actually know the itineraries, so we won't be we'll be using that instead of the model. And then there are connecting itineraries within that set. And then we have a model that will predict whether they make their connection or not. So that's the missed connection identification model. And then we have a passenger arrival delay. If they make their connection, then that's just the second leg flight delay. So that's kind of trivial. But if they don't make the connection, we have we need to predict what the resulting passenger delay will be. So that's another thing that we modeled here. And then we have these other cases. We have direct itineraries. So that's again trivial. We just convert a flight arrival delay into passenger delay directly. And another one that's not trivial and we only have early results for is the delays caused by canceled flights. So that's the overall structure. And so the next part, most of the subsequent discussion will be about modeling misconnects and resulting delays. So we'll be using some terminology here that we kind of had to develop for this particular effort. So we'll have something called the connection gap, which is the difference between the actual arrival of the first leg and the actual departure of the planned second leg, whether the connection is made or not. So basically, what is the actual time between when the first flight comes in and the second flight in the itinerary departs? The scheduled layover is the time between the scheduled arrival of the first leg and the scheduled departure of the second leg. And the realized layover is the time between the actual arrival of the first leg and the actual departure of the flown second leg. And notice that the realized layover cannot possibly be negative. All right, so just to kind of look at the data with those ideas in mind. So we have this connection gap that we just described, just to remind you what that is, the difference between the actual arrival of the first leg and the actual departure of the planned second leg. And so we can do histograms for how that variable is distributed for these two classes of passengers, those that make their connections and those that don't make their connections. And not surprisingly, if you make their connection, the connection gap has to be greater than 0. Many of the cases where the connection gap, where they miss the connection, the flight literally arrives later, the inbound flight compared to the outbound departure. So that would be a negative values on the horizontal scale. And you see a lot of the misconnections are in that category, although a good number are also, there's some positive connection gap, just not enough for them to actually make their flight. And this is showing one for the August day and one for the July day, and fair amount of consistency there. So this is looking at the basically the fraction of flights of passengers in each of these two categories. When we actually look at numbers, it's not as it doesn't look as appealing because there are actually very few of these misconnection passengers relative to the those who make their connections. So if we convert from counts from fractions to counts, the data doesn't look as conducive, although there is still plenty of misconnections so we can model it. So we have some pretty simple models. I was bemoaning to my son at breakfast today. He was asking me what I was going to be talking about, and I was going to say this thing about this talk that kind of worries me is I could have given it in 1995. He's an English major, and he said, "Well, that's great. That's modern." So these are at this point quite classical models that have been around for a long time, and we'll see they seem to work fairly well compared to more advanced models. So this is a standard binary logit model where the outcome is whether they make their connection or miss their connection. So those are the two outcomes. And here are a couple of models. The first one has this connection gap that we're just talking about, and the probability here that we're looking at is whether they make their whether they, let's see, which is it? Is it whether they miss their connection or make their connection? It's a negative on the connection gap, so that is whether they, if the connection gap gets bigger, they are less likely to miss their connection. So that's what the negative sign on the connection gap means. If we make it a look at two variables, the scheduled layover and the second leg departure delay and the first leg departure delay, that's a little more kind of complicated way of characterizing what happens at the connection point. And basically the first specification works a little better. The simpler one is better than the more complicated. So we want to see how this works in terms of testing versus training. So one of the things that we have to do with these models is choose the right sort of crossover point where we'll say we're predicting a connection being made versus not being made. And since we're trying to use this to predict delays, ultimately, we would like predictions that have a balance so that the false positives and the false negatives are of the same magnitude, so that we're not systematically making misconnections more likely or less likely. So we have a loss function that looks at the overall errors, but also emphasizes having the errors be kind of balanced in both directions. And so this is what happens when we choose the right thresholds and then apply them to the testing day. So in one case, we train on the August day and test on the July day. And in the other case, we do the opposite. And so you see basically kind of the confusion matrix, the number of true positives, the number of false positives, the number of false negatives, and the overwhelming majority are true negatives. So it predicts a misconnection. It predicts that there is no misconnection, and there is no misconnection. So that's the true negative column here. And we see that although we tried the predictions were balanced between true negative and between false positive and false negative in the training part, when we actually test it, there is somewhat of an imbalance. And if we compare the two specifications, the first specification, the simpler one, is actually better. And then what turns out to be the best one is similar to the first one, but adds a time of day effect. And we capture that by sinusoidal functions, a sine and a cosine of a time of day. And you'll visualize what those effects look like in a minute. But we keep this connection gap as the primary driver of the model. And then we add this time of day effect. And you see the results in terms of the performance of the model in testing on the bottom here. And to kind of visualize what this is telling us, if we look at the connection gap and then look at the odds ratio, based on the specification, we expect that to be a straight line, and that's what we get. So that's on the left. If we look at the effect of arrival time, that is on the right, and notice that there is a daily pattern. Notice that the scale of this plot on the left is different than the one on the right. So the effect of time of day is relatively small, but it is kind of a discernible effect in terms of when the connection is scheduled to happen. And then I said we were using very, very old models, so we tried to use a little more modern model, which is a general additive model. This is similar to a binary logit model, except it allows sort of spline function approximations of the function of the x variable instead of just making it linear. And so we've played around with that extension. And the bottom line is that it doesn't do a lot better than just a good old binary logit model. So there's not a tremendous value so far in using more advanced model, at least in this particular part. So we have a model that predicts whether people will make their connection or not. And now we need to look at, in the case where they don't make their connection, what will the delay be? And so there's more to be done here. But what seems to work pretty well is to divide the day into three parts. And we look at the arrival time and figure out which regime it is. And we classify these times of day as early, transition, and late. And if you look at, this is the distribution of the arrival delays of misconnected passengers for these arrivals before 5 in the afternoon. So in our terms, we consider all that to be early. And then we look now at between 5 and 9, and then we look at 9 and 3. And one thing to notice, and the reason why we have to pay attention to this time of day effect, is that these distributions become bimodal. Just to see if anyone's awake, why do we see these bimodal distributions for misconnections when we have these later scheduled arrivals? Why do we see that? I'm disappointed.
I didn't see this in the meeting yet.
So you've got a misconnection. You're say you arrive at you're supposed to arrive at 10 at night, and you have a misconnection. What's likely to happen? You stay overnight.
Yeah.
So that's what this is. And we see some of this here. None of it here, because these are before 5, so they can always get out. And then we see some of it between 5 and 9, and then a lot of it at this period. So that's what these histograms show, and this is just the cumulative distribution functions for these three cases here. And you again see this big difference where the green curve has a many more late, very high delays. So if we put this all together, just in terms of the misconnection part, we again are doing testing here. So we use the August for training, and then use July for testing, focusing on just the domestic single layover flights. And that third specification with the time of day effect. So what we find is that the passengers, the estimated misconnections is slightly greater than observed in this particular test. The total delay is also slightly greater, and the mean delay per misconnection is very close, but we're like maybe 13% off in terms of this results of this testing case. So a little bit about cancellations. We're not that far along when it comes to cancellations, but what we basically do is we look at all the itineraries where it turns out one of the flights is canceled. And so that can be a nonstop itinerary. So, and that flight, the nonstop flight is canceled. Or for a connecting itinerary, it can be the first flight on the itinerary is canceled, or the second flight on the itinerary is canceled. And then we again characterize the time of the cancellation based on the scheduled departure time of the flight into early, transition, and late. This was just done kind of by trial and error, finding the best times to define for these three categories. And then we just have average delays for these different cases. So basically our so-called model for cancellation passenger delay is just picking the right number from these three cases.
10 minutes.
10 minutes, I'm almost done. Summary, conclusions, and next steps.
Perfect.
So if we just look at the overall performance, focusing on August to July, including some of the numbers we looked at before, as well as the cancellations. So the question is, how well can we predict the passenger delays on the July day using the August day? And if we want to kind of bottom line, if the metric is total disruption-related passenger delay, then we're quite close, about 2%. If it's passenger total per passenger delay, meaning disrupted passengers, then it's about 5%, so still fairly close. If we look at some of the individual buckets, they're not as close. So to some extent, these are two wrongs making a right down here. So we tend to underestimate cancellation delay. We tend to overestimate misconnection delay in the order of 10-12% errors. And in terms of this, the delay for per misconnected passenger, we're quite close. So that's kind of where we are in terms of predictions. And so to summarize, in support of our CATRes mission to make the NAS more resilient, we developed a model of passenger arrival delay. The research is enabled by a unique proprietary data set. And 2 days that we looked at, the average passenger delay is about 2 times average arrival delay. When I was making this slide, made me think of 3x. Remember 3x? When, so this is not as happy an X as 3x was. The bulk of the delay impact falls upon a small set of passengers who are disrupted, as we've been talking about. And if we kind of look at the bottom line, recognizing there's more, the results aren't really as good as these numbers suggest. But if we do look at the bottom line, we get about 2 to 5% accuracy in being able to predict. Next steps, and we need to improve data analytics, I think, particularly for the cancellation delays. We have 2 pathetic days of data. I mean, they're great days, but 2 is pathetic. The number 2 is pathetic. So we're going to try to beg our airline for a few more days, maybe even some good days to contrast. We didn't talk about it here. We showed it in the diagram, but part of the effort is a model of airline disruption recovery that will be integrating this so that we can see not just what happens to the flights, but also what happens to the passengers, both in the baseline, the way things work now, and the way that we hope they can be improved by different kinds of countermeasures. And one particular example that many of us are infatuated with is intermodal substitution. So given the large delays that we just looked at, you can certainly envision situations where the best way to get them to their destination sooner is just to put them on a bus. So that's one of the kinds of things we'll be looking at. And I think that's it. So if you have questions, feel free. Yeah.
I have a question mark, and it's both for you and for like the ULI team. So I guess luckily for the ULI, last 6 months have seen two big disruptions. One was a shutdown and the next is the big rebellion. I'm wondering how much of that do you have access to see how well these work? And vice versa, are airlines expressing interest to use some of this to at least virtually test what they can have?
I think we have 304 historical disruptions when we've done that work, and the ones you mentioned are not included in that. So we're not starved for test cases for disruptions. I don't think, although we've been following these, and we actually have a paper about the shutdown disruption we've just been working on. Whether they make it into our kind of reduced set of testing cases, we haven't really talked about yet. I suspect they might not, because we don't have as rich a set of data. I think the airlines are following what we're doing, and I think the airlines do have a lot of sort of internal work, and there is issues of proprietary data. So exactly how what we do will ultimately affect or help the airlines remains to be seen. They do attend our technical seminars. There was a seminar last week that I had to miss on using large language models to create training scenarios for traffic management professionals. And some airlines were very interested in using that for training their own people for how to deal with irregular operations. So that's one example. Some of the things that we propose are hard for airlines to stomach. And in particular, my own view is that on these days of extremely irregular operation days, maybe the worst, not 9%, but maybe 2 or 3%, we create a dictatorship. We create, if you will, a Trump of aviation, and they have complete power to tell everyone what to do. This is just my view, so don't blame my colleagues for this. And when I suggest things like this to the airlines, they look at me like this slide. So there's some things that are politically acceptable that we're doing. Obviously, as academics, and part of the leadership initiative is to do things that are maybe go against the grain, but maybe in the long term well.
Dr. Hansen, we really want to thank you so very much. This has been lovely. We've got a little bag over there for you.
Okay.
But
what?
goodies.
Oh,
NAMS-2 specific essentials.
bit.
So I'll close off with the next airtime seminar. We'll return to Tuesday next week, and we will be having Susan Shaheen, who will be discussing AAM under uncertainty and scenario planning in the San Francisco Bay Area. So thank you all very much for attending.
Thank you.